Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to welcome James Noble from University of Wellington in New Zealand. Most of you know James for his ambition to control aliasing in object-oriented languages through ownership systems and ownership types and so on. But today he's not actually going to talk about that. That's amazing. So instead, we're going to hear about how to strip down object-oriented languages to their essence, hopefully, in Grace.
Yeah, sure. Thanks for that, Manuel. It's nice to be here, and to all my listeners around the world, hello. And it's nice that we're quite a small group. This is my line for being bitter and twisted, that there's 3 other seminars on at the same time. The nice thing is that with being a small group, we can be interactive. So I've got a bunch of slides, but I'm more than happy to take questions and abuse and comments and suggestions. And we'll see how we go. So what's this project and why are we doing it? Why are we thinking now about a new object-oriented programming language? And, the story behind this is that sort of the 3 of us, with a bunch of other people, I don't have all their names on the slides because there seem to be more people who at least don't think this is a completely daft idea. We're having a discussion at eCoop in Slovenia about 9 months ago, and we were all saying, well, we're teaching Java. And, it's okay, and we're invested in it. We've got a lot of teaching materials in it, tutors, everybody knows this. Do we want to be doing that in 2020? In some sense, is Java the best thing we can really do for introducing perhaps at the universities for the rest of us students to programming? And in 10 years' time, do we think that will be the case? Because in 2015, Java's going to be 20 years old. Happy birthday. Hopefully, the state of the art has advanced. And I mean, in some ways, you can see this in Java and in C#, because, well, Java's now got generic types. Important new advance in computer science in the last 20 years or something. It's now got that. That's good. Lambda expressions. There's a whole bunch of stuff. Big nums. Yeah, great. Big decimal. And I presume C# has all these things. And so the state of the art has advanced, and in some sense, Java and C# have actually advanced along with it. The catch is that from a professional programming point of view, this bit here is important. New languages are bringing new ideas. So if you like, you can write in Java, or even more so in C#, programs that are structured and use all kinds of constructs that you couldn't do it in Java version 1.0. The programs could look completely different. But of course, those Java 1.0 programs are still going to be quite legal in the Java of today, and the same thing is C# across the range. The catch is that when the new languages bring in good ideas, or the old languages are updated to include them, we've still got all the old ideas. And again, this is probably strictly truer of Java than it is of something like C#, because, well, C# had the advantage of hindsight by looking back at Java. And so what I think is this kind of compatibility problem, while it's important for professionals, is a difficulty for us when we want to teach. We want to teach programming. Ideally, at universities, we don't really want to teach a particular language, although I don't think there's any way to teach someone to be a programmer unless they learn through what you do with them and come out as being a competent programmer in at least one programming language, preferably more than one, preferably languages that are different. The point is what, using Fred Brooks's dichotomy between the essential differences, the things that make programming really hard, and the accidental difficulties, the stuff that our technology puts in the way, we find these accidental difficulties, things we know how to do better, just take a lot of time. So, say in our first year course, in theory, we have 36 lecture hours in front of students, and students do labs, and students do tutorials and other things. But that gives us roughly 36 topics we can talk about. Now, one of those topics has to be to welcome everybody to the course, and then another, and then another one has to be here's what's in the exam, and another one's the terms test. So maybe in a half semester you've got 30 topics you can talk about, right? So in Java, one of those has to be the difference between int and integer and float and double. Okay? In order to make almost anything happen with any APIs in Java, you have to explain to students what the difference between float and double and int is. Now, is this important for programmers to know? Yes, it is. Is this something that really has to be taught right at the beginning of teaching people to program? I don't think so. If you want to teach people how a Java or a C# program is evaluated, it's welcome to overloading. I really like overloading. And in my terms tests, I really like overloading because in my terms tests, I can always find really, really difficult problems for students to evaluate. A debugging problem, what will this code do? If I've got this thing in here and then I cast it to something else, and is it resolved statically or is it resolved dynamically? And I mean, were I to switch to C# 3 or 4, it would be even better because I could have dynamic variables as well as static variables, and all these things would fail in different and exciting ways at runtime. I mean, it would mean that you could have almost as much fun with method overloading as you do with pointers, but that's another story. So essentially, our project is to tackle these accidental difficulties in programming language design. Not the things that really make it hard. If you know about projects, in some ways, I guess Touch Studio is probably one of them. There's stuff like Alice and Kodu and Scratch, which are new ways of, Toon Talk and stuff, new ways of re-envisioning what it means to program or what it means to teach computational thinking, trying to find ways, let's tackle what makes programming hard to learn. Here the idea is now. For better or worse, we think the world still needs programmers. But we want to try and just clear out a lot of the cruft that has been established in these languages. And so basically over the next 20, 15 years, there's space for us to put more cruft back in. And then presumably sometime down the track, we repeat the whole process. The other thing, this is Andrew Black's slide, points out that as sort of academics or as programming language designers, we're in the dog food business. So the user model, I'll talk about that on the next slide, is for beginning students, but the people who make the choices aren't actually the students. Okay? The people who are going to make the choices are hopefully experienced instructors in programming language or faculty committees or these kind of things. They're the people who are actually making these choices. And that's something, again, that we keep in mind. So it's not necessarily... And you'll see some of the choices because, we're academics and we also have ideas about how things should be done. But this isn't just about what will make it easy for someone to get things started. I suppose it's also about what will tend to encourage people to develop what we hope will be good habits or good practices as they go on. So what is our user model? Well, there's Fred Brooks' latest book says every project should have a user model. So I think I was reading it at the time when I was doing this. First or second year students in OO, CS1 or CS2. So this is an attempt at doing another OO language. Okay, if you go to CMU, Bob Harper has got existential type blog, all kinds of excellent examples why object orientation is dead and why teaching OO languages would be like teaching assembler at first year, etc., etc. We're trying to give him a run for his money. We think that there are a lot of things that perhaps people think are wrong with OO languages that are wrong with OO languages that we tend to use often. So assuming you're primarily interested in OO, the other thing we're willing to say is, but even given that, is the sort of overall approach, there's actually a whole range of different pedagogies that people can use when they're teaching. So, objects early or objects late. If you're in this business, some people think, well, you can start out by teaching objects. You can start out by calling a message on an object. You can have a little car or a turtle graphics. You can start doing all this stuff. And you can really get quite sophisticated if you've got libraries before you have to start teaching about control flow or mutable variables. You can have mutable objects, but you don't have to teach about the details of assignment. Or maybe you just want to start off with control flow and more or less teach the same course that people have been teaching since 1970 in Pascal. Here is a variable, here's an assignment, here's how you create, write the greatest common divisor algorithm using a while loop and using an if statement. So the point here is that this language is trying not to buy into a whole lot of assumptions about pedagogy. And this is different from other projects which we like and admire. The type scheme project, the Racket project that it now is, with how to design programs, Matthias Felleisen and his students and collaborators. They've got a very set idea about the pedagogy. It's functions first, it's no immutable state first, and a strict progression through the languages, and very nice environments to support that. But it's not just enough to say, well, there are nice things in this environment. You have to say, and I'm going to teach this in the way that Matthias Felleisen has decided computer science must be taught. Okay, and we're being a bit more relaxed than that. So static or dynamic types is another argument here. There are lots of people who think static types are important, they will catch errors, and so students should start with static types. There are other people increasingly saying, well, you know, actually it's important that students are able to type something in and at least make something happen, even if that thing that happens is a crash, rather than sitting there for hours and hours trying to get the red lines removed from under their code. You know, and there's always the famous story of someone who comes in and comes to the tutor and says, well, I've been working on this for 3 hours and I finally got my program to compile. But it doesn't do anything. Why not? They've commented the whole thing out. That's right. Excellent. So going to dynamic types first, for some people, certainly I know many places. I mean, I think MIT started with Python. They moved from Scheme to Python. Quite a lot of other places are saying, well, look, we'll do the first semester in Python and then second semester in Java, precisely to give this kind of smoother ramp into programming. The catch is that, you know, in the 30 lectures, if you're lucky, of content in the first course and the 30 lectures into content in the second course, a lot of these things are going to be, okay, kids, well, here's how you used to do it in Python, and here's how you do it in Java. Here's how you used to do it in Python, here's how you do it in Java. There are some advantages to that. I do think people need to learn more than one programming language. But if you're saying, how do you get school kids who increasingly, and I mean this is something Touch Studio is trying to address, increasingly come with no exposure to programming. In New Zealand, the only people who even do higher mathematics at secondary school typically are those who want to go on to become doctors. So they're not great at mathematical thinking. In my generation, I was at the Computer Museum last week, and yes, there were all the ZX81s and the Apple IIs where my generation started. You'd plug these things in, turn them on, you get a basic prompt. I think I was talking to Manuel and said, if you want to play a computer game, you've got a book, you've got a magazine, and you had to go and enter the listing into your computer, and then you could save it onto a cassette tape. So there was, you know, even if they didn't think about it, they were at least having to type in programs and hit run and fix syntax errors, perhaps. These days, we want to make an easy ramp. And then, yeah, there are other approaches. Perhaps you do want to start teaching some form of functional programming first, procedural programming, scripting first, a bit like could be a bit like objects, just writing little scripts to do things. Software engineering first. Maybe you're going to be hardcore and say, okay, well, the most important thing to teach is the notion of a precondition. And if the programmer can understand the precondition and the postcondition, then everything else will be fine. So, you know, is this an ambitious goal? I guess the point is to say, we're trying to cut down the things you have to believe that you could adopt this language. And the reason is because I think one of the strengths of languages like Java and C# is, in fact, people can do all this stuff, more or less, with Java or with C# today. And, you know, one of the ideas underlying this project, and I've got, you know, other things down here, researchers wanting an experimental vehicle, language designers wanting a good example. I think it is important that, you know, there is some sort of form of code, and it's going to be, as you'll see in our arms or something like Java or C#, that people can read. You know, the more we end up changing the languages we teach, the more different computer scientists are going to be, you know, across the country, across various schools. And I think we do need some kind of common language. I think there often always is a common language that by default, if you read a paper or read a journal article, you know, at some point it used to be Pascal, and then it changed to sort of C syntax and has more or less carried on from there. And, you know, it might be Java, it might be C++. The details aren't important. The sort of common ideas are there, which means that there's some kind of code we can expect most people to read. And if one school's mostly teaching Python and Ruby and somebody else is teaching Haskell, so this is my constellation of languages slide, and the first time I did this talk, I talked for 10 minutes on this slide alone. It's a bit of a setup, you know, power and complexity, and PL1 lurking out here with extreme complexity and low power. If there are any PL1 programmers in the room, you'll probably dispute that. And, you know, quite why I was so mean to ML over there, I'm not sure. The sort of Java Haskell thing is, sorry, Java C# is sort of going along here, and F# comes in, increasing the complexity and also increasing the power, probably not quite as much. And then in some sense on the other side, well, let's ignore CLOS and these beasts up here. You've got things like self and Smalltalk and Scheme, dynamic languages, which, you know, yes.
You really are going to have to define power.
Sure. I think all these languages are Turing complete, with the possible exception of PL1.
No, define power.
So this is clearly subjective. It's just my idea of sort of how much the programs can sort of do if you write them. I mean, it's not. The real point of the slide is this. If you can think of another word than power here, you know, it could, I'm happy to have suggestions.
So how much work does the program have to do?
How much? So perhaps power to weight is better than just straight power. How much work does the program have to do to get some kind of effect? That, yeah. In wearing one of my other hats, you know, I'm enough of a sort of software engineer that productivity could actually mean something real. I mean, you're on a good point there, because I basically pick power on the grounds that it doesn't really mean something real, and complexity as well. While Martin Odersky does like the metric of the number of keywords. Actually, Rob Pike primarily likes the metric of the number of keywords in a language as being an indication of its size. I'm not entirely sure that's true. Really what I'm trying to get at is, okay, so there are these things. I mean, so for example, I said processing is more powerful than Java, even though processing is basically Java, because it comes in an environment with a whole bunch of libraries for doing processing type stuff. So in that sense, yeah, you're right. How easy is it to get some effect? What's interesting, though, is if you start having a look at some of these things, if you say take Smalltalk and Strongtalk, if you don't know what that is, that's a statically typed version of Smalltalk, or something going quite the way to statically typed. And you've got Ruby and a statically typed version of Ruby. In fact, there is IronPython and PyPy. PyPy certainly is Python with added on static types. So on one level, you've got this stuff, these statically typed languages getting harder. On the other side, you have languages that, you know, started out as hardcore static types, which are starting to add things like dynamic. Okay? And if you look at some of these languages, like if you look at the relationship between the language by type systems, what can you say? Well, most of these kind of languages are going to have a type system that, you know, it has got generic types, has probably got some form of structural type matching, even Scala will do that. Perhaps has got intersection types. And then often for Python and Ruby, there's a whole lot of weird stuff bolted on the side for the very incredibly strange way the libraries have been designed. If you look at Michael Hick's papers, he's got some wonderful examples. So I'm kind of wondering if there is a gap, and of course have set up this slide so there is a gap, which says, could you have a language that on the one side takes the heritage of things like Java and C# and perhaps Pascal before that, in terms of doing things that are clear and trying to make things explicit and, you know, start to establish good discipline and good habits in programmers. On the other side, draw on the heritage of these dynamic languages about giving power with simplicity, about people being able to get started. And, you know, this is another argument that, in fact, there might be some sort of compromise proposal that can go in here, which is what the rest of the talk is about. So getting into some actual design details, what kind of fundamentals do we have? Everything is an object, single message dispatch, single inheritance. This notion, again, imitation is the serious form of flattery, and we think the stuff that Matthias Verleisen and co. in the Racket project are doing is great, how to design programs, etc. Extensible via libraries, again, also there, the idea that, I mean, this is something, again, in teaching that is important, and why, for example, our language needs some kind of support for libraries, because a lot of what tutors and staff members do when they're teaching programming is set up particular little problems or libraries to do graphics or libraries to model this and that people have to interact with. And then there's this last point, which is also quite important, that Java, C, Python or Scala programmers should be able to read, and I probably should have said write as well, grace programs that if you look at this and you think, wow, it's nothing but a bunch of parenthesized expressions, you're unlikely to be able to read this stuff. If you're an instructor, the dog food problem, you're less likely to be able to adopt it. But also, people who've learned to read and write Grace should at least be able to read most of these kind of things. The look of the language, the feel of the language can't be too foreign from where people are at now, because there is a large amount of code in the world that is written in, using a very generalized sense, the sort of language tradition that produced these kind of things. Again, we're not going after the essential difficulties of programming, we're going after the accidental difficulties of the language in, I guess, the imperative object-oriented tradition. So what does it look like, the big reveal? No, that's not the big reveal. I might ignore that and come back to it. There's the big reveal. No semicolons. Right, so what I say about this slide is, if I have to explain it, the project's already failed. I've just explained how important it is that people can read these programs, can read and write Grace code. Are there any questions?
Well, you may have to explain why while and if look so different.
While and if look so different. Okay. That is fair enough. Yes, in while you have to have these curly braces here.
You need to have the do keyword afterwards.
And you need to have the do keyword up. Yes, you do. Yeah.
And you have those then for if. But,
yes, you do.
all of those languages that you're familiar with, while and if, look the same for
they do.
conditions.
Yes,
together.
yes, that is a difference.
You may want to just remark on that.
Yes, I could just remark on that. Was there another question?
Yeah, why do you need to declare the return type, but you don't need to declare the type of locals?
The type of?
The return type of the method.
Okay.
That's number, but the locals don't have to be declared.
No, they don't. So, answering questions in the reverse order, we think it's important to declare the type of method parameters because that's an interface to the method. These locals are internal, so what we will do is probably local type inference here. So in that sense, this is, remove that colon, and I think the meaning is the same as it is in C#. Just goes that way. There is a syntax if you want to. If it's not obvious from here, you can put a type on this. You can put a type and also initialize that if you want to. Good, so I'm relieved. You can at least read all the code if you're not sure about the design decisions. Do I want to talk about this? Well, we'll talk about that. We'll come to that. We'll come to that. So what features can we see here? Well, these are the things we wanted, and part of the rest of the talk is actually going to be about how, so far, which ones we've had to give up on, more or less. Uncluttered code with significant layout, structural typing, a bunch of stuff that, again, is in the current generation of languages that people like. Basically went through a long list of features, and every one that people think are good we put into the list. It's kind of an odd way of doing things. Subtyping separated from inheritance, user-definable operators that ones people can understand somehow, generics. Allows both static and dynamic typing, and that seems to be one of the, surprisingly enough, there have been research languages that have done this. I guess there's dynamic in C#. I suppose we're trying to go further than dynamic does with C#, but also we're increasingly aware we are butting up against stuff that's really only been done in research languages, particularly there. And these various things, important for teaching. Minimize the number of options. Rather than having 2 or 3 choices about how you write a bit of syntax, we'll have one, and maybe that means things are a bit longer than they need to be, but people don't have to worry about whether you write an equals in an expression or a curly bracket and a method body in a closed curly bracket. Minimize magic implicits, implicit conversions, not throwing back to any particular language, but C#, C++, when I was teaching that, trying to explain what on earth is going on with copy constructors and conversions and all this magic stuff. There's nothing there invoking them. That's difficult to explain. I mean, it makes for great terms tests, once again, but... And minimize incantations. So, why do you have to write public static void main? Why do you have to write class curly? Well, because it's Java. And maybe it is important that one of the very first things people learn in order to get a computer to do something is, you basically have to get your prayer in exactly the right incantation to some strange god that lives in the machine. If I don't say public static void main, which means almost nothing I just have to say it. Why? You just have to say it. Let's not do that. So, the basic idea is, well, what I now call one true method request. So, like Smalltalk and Self, and also like Go, we won't overload anything. Okay? The computational model is we have objects, a method request names a method and provides the arguments, and then a dynamic dispatch in the object selects the correspondingly named message in the receiver. Okay? And then the method executes in the receiver. Now, this is basic. This is a simple story. This is a story that is true in Smalltalk and Self and not true in lots of other languages, because you've got overloading resolution, you've got static typing getting in the way, all these kind of things. Okay? So the idea is there'll be a nice, clear operational model with nice, clear semantics of various kinds that we can explain and understand what programs are doing, hopefully in a way that people will be able to understand and follow. Yeah, we're trying to learn not to say method send or method call. There's a certain Smalltalk heritage lurking under the surface that is about to raise its head, I think. And we're trying to, method request seems closer to what people do in Java, and these days if you say message send, half the people think you're doing actors anyway. So, what do method requests look like? Well, they look like Java. You can write a person.print on output stream, or yes, we do implicit self, print on output stream. We've got operators, x plus y greater than z and not q, boom, boom.
Are these method requests?
They're method requests too, yes. So there are 3 syntactic forms, more or less, for method requests. And in fact, there are 4 different kinds of method requests, but that's no more than Java. And currently 1 less than Newspeak for anybody who's counting. If we want to go into that, we can go into that. Okay, what about this for loop? And this might answer some of the questions. Well, like Smalltalk, we've got multiple keywords. So, we don't have to do it this way, but, for, do. This is seen as a single method request for do that's on self. Okay? That's a method request between integers that builds a range object. Yes?
And is it half open?
Half open.
It includes 1 but excludes 10?
I think currently it's probably the whole way.
You'll rethink that.
We'll rethink that. So the other issue is where do collection indexing start from?
Actually, this means 0 to 9.
If you want it to mean 0 to 9, you write 0 to 9. I'm tempted to say which bit of we're going to try and make things explicit and mean what they look like. Unfortunately, you can't have one of these things being a square bracket, one of these things being a round bracket currently. I'm sorry. And
But you can still redefine dot dot.
you could certainly still redefine dot dot. And I encourage you to do that. Yeah. And this is the way you write a for loop. And one of our bets is we will tell students, it's a for loop book just across obviously the numbers from 1 to 10. We don't think that there is any more magic in writing this than there is in writing for I gets 1 to 10, or for number colon I 1 to 10, or for I equals 1 to 10 do print I. We think that we just tell people in the first week, you just have to do it this way. It's evil magic. Okay. Except, of course, well, if it is evil magic, that's a Lambda expression. And this answers your questions about the while. That, that's a Lambda expression. That's a Lambda. So all the blocks in code, this one in Grace, they're all Lambda expressions. Many of these are these strange no-argument Lambda expressions, which you get in imperative languages, but you tend not to get in functional languages because there's no point in calling a function if you can't really do anything.
So you said that if then was a method request on self, right?
Yep.
So does that mean I can override what it means on any class?
So the answer is currently perhaps. And the reason we're doing this is because to get extensibility. So one of the decisions we've made, for example, is we're not making any choices about concurrency into the initial language. So where we're up to at this point is the sequential core, and we're hoping that a whole bunch of stuff can be added by extensions. So most of the time if students want to override this, they'll probably should get a message saying grace.standard prelude, if then else, is final or something like that. We probably won't use the word final. So you'll get an error for trying to override if. But if Ruston really wants to do this, and he runs his code with something else that says, by the way, we're in Ruston world, not standard Graceland, then you'd be able to do it. And the other, I'm not sure where this comes up. I mean, the other advantage is the claim Smalltalk advantage is, if you want to show how this works, you can. I think the blocks probably come on a little later. If you really want to show that in this language, if is encoded roughly the way it is in the untyped lambda calculus, well, you can show the code.
Yeah. If the loop body is always a lambda, can you have a break?
So again, this is probably still the one thing that's left on what to do about syntax. Currently, we don't support break and continue, but as Dave Ungar explained loudly several times at the meeting I was at last week, and we already know how to do this. You can basically add an extra parameter into the lambda which captures a closure with a return in it, so basically an exit. So if you want that, you put an extra parameter in here that is E for exit. The type system such as this will ensure that you're calling the right thing at the right time, and then you evaluate the value of exit and come out of the loop. So yes, so the question of non-local exits and what more than just lambdas for control flow we want is something that is still on the list. And if lots of people say, well, you really have to have explicit exits, then we'll put them in. For quite a long time we had an explicit loop with exit construct, and then we thought, well, does this mean if they're nested, what happens, and do you have to start naming the loops? And so this is where we're at now. How are we going for time? Other decisions. This one I call Lisp 1 versus Lisp 2, which is a kind of a retro name. Basically, the point here is that variables and methods share the same namespace. So if I want a variable, I can get a variable type 3. If I want an accessor method, I can just return that variable. If I want to set a method, I define a method with a slightly odd name, and it can set the variable. But in fact, you don't need to do this, because in Grace, the myxy variable is accessible as if it was defined by a method called x that read the variable and a method called myx : equals that sets the variable. Okay? So this is, at this point, setting aside issues of encapsulation and private and protected. We know we're going to have to deal with that. The design isn't finished there yet. So one advantage this has over languages like Java and I guess C# is that people don't have to write the accessor methods. We don't have to add extra mechanism into the language to generate the accessor methods if you want them. And we can have the advantages of them relatively lightweight without having to add other features to the language like attributes where you can override the getter and setter on the variable if you want. We just have methods, we have variables. And here's one of the examples of, if you like, the technical theme of the talk, which is the way some of these decisions then flow through. So if, for example, self was required to be explicit on every message send, like in Python, and if you required parenthesis, to square the variable x, you'd have to write something like this, okay, which, well, looks a bit ugly and messy, and we want to write this, okay? So this decision saying, all right, we're, at some level, this decision, we're going to have a single namespace for methods and variables. A field basically is something that can be accessed by two methods, means that it then flows on to have issues for the syntax. Yeah?
So you can't have first-class methods now.
We can't have first-class methods now.
Because you can't distinguish anymore whether I refer to the method X or whether I'm actually calling it.
Right. Yes. That's right.
So you made it assume that you're never going to need to be able to name a method.
No, but where do I get there? Can we hang on? And I think there's some. Yeah, I'm going to. So yeah, that's one place that comes back to bite us. Types. We're going to have types. This thing clearly creates a variable called Gerald and explicitly gives it the type person. This one down here sets a variable called Gerald and puts person into it. But this one probably should be dynamically typed. So, unlike C#, we don't think we can ask people to write dynamic on dynamically typed variables. Why? Because the whole rationale for having the dynamically typing in the first place is so that initial students can come in and can get their programs going, with as little bugginess and as little syntax as possible. So we don't want to say, by the way, you declare a variable called Gerald by, you have to type :dynamic. Why do you have to type :dynamic? You just have to pray to the big god of the compiler, or the big god of the IDE. So our current line is that in Grace, names must be declared. So this is unlike Python, where you can magically create new fields from a misspelled assignment. There's however many years of software engineering, I think, still teaches us that being able to implicitly create fields and variables is a bad idea. In Grace, types can be omitted, and they may be dynamic or they may be inferred, and that looks like being context sensitive. And again, we'll have to see how well that works. Our eyes are getting used to this, so we write stuff and we think, oh yeah, this is all how it should work, and then we try and implement it and find out it doesn't. But this kind of choice here. Now this is different from Scala, where types may be omitted, but the rule is the compiler always will attempt to infer types. Scala never goes to type dynamic, which means Scala always at least has the compiler's idea of what the static type of any particular expression is. Okay, in Grace that's not the case. And so the question, here is what should this do? Should this create a dynamically typed variable and stick person into it? Should this locally infer? And that's something we're still debating. I probably think, well, locally infer, in the hopes that generally people aren't going to be in a situation where they're initializing a local variable with something that is, a very specific type, and then they're going to want to reassign to a more general type. But, we'll have to see.
So might the behavior of the rest of the code be different whether I choose option 3 or 2 there?
So that's one good thing, and this is where that one true message send rule comes in. The behavior of the code won't be different. But the behavior of whether the program is a legal program or not will be different.
That's basically why you throw out overloading.
That's why we throw out overloading. That's right. So in that sense, well, there's Gila Bracha talks about the condition that program execution should not depend on static types. Okay? And the point here is we actually go one further than that, which is that parsing can't depend on static types. All right? And this is where your point comes in. Because whenever we see an expression, we have to be able to parse it. Let's skip that. That was mostly why it's hard. Where is it? Let's skip on. Skip on. This is... no, I'm completely lost. I'm sorry. This is going to look good on the video. You're seeing all the slide. Right. So this comes to your point about methods, which is we need to be able to decide that purely syntactically, and basically we can't. This was just some other hard cases for the type system, and discussion with Mads Toft yesterday. What should 3 plus Cucumber new do? Is this a static type error, or do we magically decide that somehow it's being dynamically typed?
According to your rules, it would be a dispatch of the number.
Right. So, yes. The good thing is that if this expression is formed, there will be a sensible execution, and that's an important property. There's still a question of whether we decide to signal a type error for this or not. And at some point I say, and what happens with that type error is really up to the programming environment. Well, what I think we need to do is, or we plan to do, is define the language so that there is a type system. And this would presume, and I guess under most type systems you can think of, unless for some reason Cucumber new is returning something of type dynamic, this would give a static type error, or it would be an error in terms of the type system. Right? Now, because of the one true method send rule and because of this decoupling, yes, there is a sensible syntax, and yes, you could go and run that if it's syntactically correct. And at some point, this now comes up to these options about pedagogy. Just because you could sensibly run the program doesn't mean that an instructor might want you to run the program. They won't want you to get everything type safe first. Okay? Martin Renard has a nice project called Ductile J, which provides this for Java. He's basically going through and effectively adding stuff into the Java compiler so that basically anything that's half syntactically correct will compile and can be run by pushing all the tests off to runtime. This is another one here. If you have a method in your API called drawString of list figure, and you make a list of objects and stick figures into it, can you pass it in here? Okay. And this relates to the dimensions of how much and how deep your dynamic type checking is. If you do an eager type check, presumably you will just say, well, look, list of object is not compatible with list of figure. So even if this stuff is all dynamic, actually that one is static. So this could give a static type error here. Even if we made this dynamic, then presumably we could get a dynamic type error here, even though everything in the list is a figure. And this is actually a question that we are literally thinking about right now. We're happy for suggestions. If we say, okay, you want to deal with real typed APIs, then you just have to remember to write list figure in here. There won't be any other type checking, but you'll get dynamic type errors, which will be really easy to explain. Oops, you made a list of object and it's a list of figure. And at some point you'll have to get the idea that, well, because in Grace, like in C# and the .NET languages, the generics are really reified, you have to have the right generics in the right places. Okay? Now, there are other options. Those other options are more complicated. One is, which I think the DLR will in certain cases do, is you do something to actually kind of turn your list of object into a list of figure by changing the generic in such a way that every time you access a figure, you check that it is a figure, or you throw an exception or something, even for later dynamically, rather than checking hard at the boundary here. And type bracket, I think, does something similar in these circumstances, but they can be even more flexible. These are open questions, I think, still about language design that we are struggling with. And I think Manuel's point there that we do have a semantics for this, we can run things if we want to, is important. It's a minor point. So this is the slide about blocks, which you all wish we should have had earlier. So again, this is a design decision that comes right out of the Smalltalk tradition of languages. Anything in curly brackets is a block. So the distinguishing syntax for a block is not the arrow like it is in Scala, or I think C#, it's the curly brackets. And you can think of this as defining a method called apply, which just an object with a single method called apply, which has this and runs it. Okay? And you call it like that. And so this is the ambiguity we were talking about. You have to write block.apply here, because if you're able to write something like that or with no arguments like this, what are you doing? Are you calling a method that returns a block? Which you can do. You can have a variable of type block. You can store a block into it. And you call block and out it comes. Well, when does it run? In this case, it runs when you send apply. Okay? There are stuff we can do statically, even in the dynamic type language. That's what this was about. So if someone does this, or if they write while with the brackets in the wrong place, we're hoping that statically we will be able to provide useful error messages about this. If then will be defined on self or somewhere lexical, there'll always be a definition in scope that will say this thing needs a block. Well, I'm not passing it a block. I'll at least get a static error there. Or maybe if you've got, treat all static errors as warnings, I'll get a static warning, and then you run it, and then you'll get whatever print 3 will happen, and then this thing will try and send apply to it, and you'll get a message that says doesn't understand apply. For those of you who are hardcore, sorry.
Question from earlier. So you have these blocks which are basically anonymous functions
Yeah.
that you can define, but I cannot refer to an actual named function and use it in place of a block. So you always have to edit convert everything. You don't want to do that.
Right. So what you'll have to do is use the block syntax and just define a block that takes arguments and feeds them in. Yeah.
So you figured that was...
Well, that's good enough, and again, that's the Smalltalk thing showing through. And the answer is all we can add in one extra bit of syntax, which will have to be a magic syntax precisely because this is saying you can't do it in the standard syntax. But I think VB has the same problem as this, according to Mads. And so he has an address of operator, I'm not sure what it's called, that you can apply to a method and get you the thing. In one of the earlier designs, I put that in. I think it was going to be fn, so you just write fnb, and that will get the way we'd explain it is this will get you this block, which we can write down like this. It's just shorthand. Scala, of course, uses the underscore. So in Scala, method name underscore reifies it. It has exactly the same problem. And it keeps its complexity count down by using underscore for a large number of different things in the language design. And let's just say that one was kind of non-obvious, but there are even more fun things that Scala does with. That Scala has several different solutions to this problem, but actually has exactly the same problem. And again, this is a case where aiming at different audiences, the two languages are making different choices. And we think that having an explicit apply, that you have to write. I mean, there's some code doing fairly hairy stuff with blocks. And if you're the kind of person who likes the untyped lambda calculus, this is the encoding of if more or less from the untyped lambda calculus. And then we'll have methods on. This will be a Boolean, and it understands the method if true else. And it takes those blocks and it just does apply, while loop, standard tail recursive while loop. How much is writing that going to basically put people off the whole idea of using the language? Well, we don't know. We'll have to see. Occasionally we're kicking around other ideas for other syntaxes like this, but at this point I'm still keen on this one. How are we going? So here's some examples of things where we backed off, or here's one example of something we backed off. The original version of the language said, yeah, let's just put everything in from every language that everybody likes. And everybody likes Python, right? And Python syntax. So we'll have syntax like this. And not only are we doing semicolon removal or inference, however you want to call it, or insertion, we're also doing block insertion. Okay? So somehow the tabbing will tell you this is a while, we're in the middle of a method, and this isn't just an argument, this is an argument that needs to be in curly brackets. How? Remember, we want to do this without necessarily having any static type information. I don't know, by counting the number of spaces, maybe if it's even, you could put the brackets around here, and if it's odd, you couldn't. And I had convinced myself that it was possible to have an algorithm to do this, and then spent several hours on a plane trying to write it out, and left the notebook in the transit lounge in LA in February. And yeah, we think this is probably an idea whose time went about the same time that we thought it up. Because while it might be nice to do this, having these explicit blocks in order to explain what a while statement is doing, and as Andrew Black says, well, these braces, we think of them as suspenders because they suspend the computation. Makes things explicit. And this kind of magic, well, was that went in, that went out. But we're still going to have a Python-like rule which says it's a syntax error if the indentation that you actually have is inconsistent with your bracketing. Okay, so if you start everything in the left-hand column, not a problem. If you put the brackets in here and laid it out with brackets, not a problem. But if you left out the brackets and wrote, or if you put the brackets in and then move this thing out far to the left-hand side, you should get an error saying the bracketing is being done inconsistently. We don't know how confusing that's going to be for people, but we're at least going to run with that and see how it goes. Here's another one, Ruby and Python. What does this code do? ABCD, can we write it? What would it do? Could do lots of things. This is in some way the Smalltalk interpretation, ABCD. So you send a method D to C, and then you send, I give in. You send A to self, you send B to A, you send C to B, you send D to C, which is this one. Scala, and at least one version of Grace, where we tried to get rid of the parenthesis by saying every argument is, every function takes one argument, which is actually Fortress's rule. Every function only ever takes one argument. If you want more than one argument, you pass a tuple. I think ML might technically do the same thing. Okay, so we do that, and in which case the interpretation of this is this, which is kind of odd for a more object-oriented language, especially when 2 out of the 3 people have enough Smalltalk smarts to always read it as this. So the current compromise, and it is a compromise because, again, it's a learning language, is you can omit the parenthesis when there's one argument and when that argument's a literal. But otherwise, you put the parentheses in. So you can write print hello world. And we'll probably put some kind of insertion syntax here so that beginning programmers can print A plus B equals C, and just by inserting stuff into the string. And it's important, it's clearly important for control structures that you want to be able to put in these blocks without parenthesizing them. And following Groovy, it would not be inconsistent to allow you to have, if we wanted to go to the standard if or while syntax, it's not inconsistent to say, okay, you'll just write a block and that you have an expression and a block and then another block and an expression, and they don't have to all then themselves be in another parenthesis Lisp style. That wouldn't be inconsistent. But it's not a great rule, but we think it captures most of the common cases here. But the other side is it, once again, tries to make things simple and tries to remove the ambiguity in what people write and what it's likely to do. So what time should I? Yeah, sorry.
I have 2 questions. One is, what kind of parser are you writing to read this syntax? And I assume it probably won't be in that first compiler class that you're going to teach after the CS2 class. And the second question is, what kind of contracts do you have for parallelism?
Good, both good questions. So the answer is this parser is straightforward. What kind of parsers are we writing? We do have various people who are doing implementation. So one thing that's different about the Grace project is we're not trying to produce the one best product, at least not at this point. It's the old 1960s strange idea that, well, you want a specification for one of these things and then you have implementations of the specification. They're actually different. So I know that Andrew Black has I think there are at least 2 parsers that have been done with parser combinators, one in Smalltalk and one in Scala. And I've got a student who's working in LLVM, and he now has a slightly bootstrapped sort of mini version of Grace written in itself. So I presume he's just using a recursive descent parser. But if you're familiar with Smalltalk, this syntax is very similar in spirit to Smalltalk syntax. You can parse it recursive descent. You can, it's much, we think, because the keywords are in the right place, and because there isn't this issue of names which can be used to define being used to indicate syntactic categories that you have, for example, in C++. So once you've defined something as a class, you can just use it, and it creates a new syntactic category. And the kind of things talked about before, that the parse of this can be done by a student in their notebook without having to know the static types. And we think this is good. It's, I could imagine giving students exercises which say, here's a line, draw a parse tree. Okay. Now that's for most expressions, this will just be relatively straightforward. But I wouldn't really want to do that in Java because, first of all, you'd have to memorize 20 different operator precedences. And then if you said, OK, go on and explain how this little bit of Java is executed and there's some message sends that are overloaded, I mean, yes, it's good to do this because it makes programming hard, and this means that people who aren't very good will fail. But, yeah.
So how do you deal with plus and times precedence?
So currently, I did lie a little. Currently, the spec says that plus and times and minus and divide have the usual precedence above all other operators. All other operators have the same precedence, and you must parenthesize. And all operators have the same precedence. It's assumed that they associate what, to the left, and to the left. It's assumed they associate, and there's no precedence. So this is basically the rule from self, which I particularly liked, which says that if you want to have different operators, you must parenthesize. And other than that, if you write A plus B plus C, it means exactly the same as A dot M open paren, B dot M open paren C close close. So okay, so there's a few other slides, mostly with jokes. This one was my last attempt at booking a ticket on the Eurostar with a credit card issued in New Zealand. We're doing the obvious stuff to get rid of no pointer errors, not having a nil, having ways of putting in null types if you really want null, and probably having a special uninitialized value, and it's always an exception to access an uninitialized field. One thing I haven't talked about and won't talk about in any real detail is how you declare objects and classes. I mainly put these slides in because some people said the last time I gave the talk they thought that Andrew Black and I were talking about completely different languages. We're not. I've mostly been talking about the message syntax inside methods, but we will have object constructors that you can run to construct objects. Funnily enough, we'll have classes, which basically take a parameter for one constructor method that you use to create lots of classes. And there is, in fact, an encoding or at least an explanation of classes in terms of objects. And the important thing from a software point of view, engineering point of view here, is that the method new applied to some class is not a special thing in the language, and that there isn't a static side and a dynamic side to things like there is in C# or in Java. You create an object by a normal method. If you want to substitute something in there, if you want to build factory objects, you can go right ahead. I'll leave this. This was the obscure part of pattern matching. So again, following Newspeak and Scala, we'll have a pattern match construct that will basically work inside methods in the language. We won't allow clausal method definitions. And this was briefly how it was designed using message sends. You can always. What are we currently doing? Well, in some sense, we think we've mostly finished the issue of designing stuff inside methods. The one big question there is, do we really need something more with control flow? Do we have to have call CC or something? Question of types, structural and nominal, or structural versus nominal. Originally, we all agreed on it being structural types. And then we've had 2 conversations with Gilad Bracha so far, who's had lots of experience with doing real programming with structural types in Newspeak, and basically said, well, the problem is the error messages you get are completely rubbish. Some type which is a parameter of this structural type which has this form doesn't match this other type which is a structure of this form on a parameter here somewhere else. So we're thinking about this. This issue again I've talked about, how do you actually match the static and dynamic types? Where do you decide to use type inference? How much does this matter? And modules and encapsulation. So in some sense, this is some of the other stuff that we're not planning to put in particular language features. But I suppose you could say what we're trying to do is clear a space so that these can be added in as language extensions if absolutely necessary. But one of the goals of this project is to see how far you can get when really the only language extension message you have is libraries, is being able to pass in blocks as arguments. We don't have a tower of macrology like you might in Scheme. And this is the answer to the question of parallelism and concurrency. What we have done so far is get it all out of the language. So you don't have wait statements, you don't have locks on every object. The question then is, okay, how do you get it back in again? And all I can say is it's on the list, and once we've got the next stage done where we have some idea of the way the module systems will work, one of the things that I'm certainly going to want to do is at least start sketching out how various forms of parallelism could be defined in this sort of way. I mean, we've got blocks. That for statement just takes a block. So clearly, being able to run parallel accumulates and parallel map reduces and stuff off collections is at least going to be syntactically easy to express. Whether we can do the kind of stuff that Fortress does, with splitting and merging and more complicated analysis, I'm not sure, but we'll have to see.
The memory consistency model?
Memory
declared before you even start the parallelism stuff, because if it's not in there, you're going to do Java's mistake.
Right. So
not defining it early enough.
So, whoops, we'll leave that. Leave that. That's right. The main point. Well, sorry, I have to. In my defense, I'll say I usually use PowerPoint. We're not done yet. And so one of the things I keep saying, and really is true, is that one of the reasons I want to be here today and want to give this talk is because we want to know what you think. We want to know what traps we shouldn't fall into. So far, I've been assuming that we don't want to make Java's mistake, that we'll go and ask Doug Lee and Bill Pugh what we should do. I talked to the X10 people, talked to the Fortress people. And that's what we plan to do. And at this point, the question really is, are there any decisions we've made thus far which are committing us to something in the memory model which is going to come back to bite us later? And so far we've been saying, we're designing the syntactic syntax and working out how to do the basic stuff. And I don't think there's anything there which will bite us. But if we really need call CC, or we really already need to be thinking about some of these things, we hope that the language surface syntax will be flexible enough that you can express software transactional memory if that's what you want to do. If you want to do traditional Java or C# style locks on objects and synchronized statements and synchronized methods, you'll be able to declare those in a library and metadata, and they'll go in nicely. And then, of course, there's the issue of how do you execute all of these things underneath. The idea very much is to teach a core language that can relatively easily be pushed into these areas, so that if in a second half of first semester, instead of using the time to teach people the difference between Java syntax and Python syntax, you could actually use it to say, oh, by the way, for the last couple of weeks, we're going to be looking at some of these issues with parallel algorithms, and here's STM, and you just write atomic or something, and off you go. Yeah?
Which applications from popular courses have you implemented or tried to write down in Grace? So like MIT's Python course has a bunch of game things. Can you write that game in Grace?
At this stage, we haven't tried.
A good exercise is to try to write it down, just to see like, can conceive of that.
Yes. So again, I think Kim Bruce has a couple of students that he's got interns working for him over the summer. And I know that one of them is going through his course material, which I think is basically data structures course, and trying to get those into Grace. And that'll be an interesting exercise because I think they were originally done in Scala, and so he's pulling those into Grace. But yes, doing that kind of thing, doing the basic hello worlds, that's probably very good stuff. How to design programs was something else we're going to go after. Yeah.
Do you have any experience yet showing this to inexperienced programmers, like seeing how they react to error messages and so on?
No.
I'm wondering if that would feed back into the language design.
Well, we hope that it will, but we're trying to get somewhere first. And the other issue is at this point, we're looking at doing it. So this is again in the same way as multiple pedagogies. At this point, we're trying to define a language and not just define an environment. So we can say we'd want something like processing, we'd want something like BlueJ, we'd want the Eclipse plugin, ideally we'd want a Visual Studio plugin, but where was it? In as much as this is a serious project, the time scale for those things is 3 years in the future. It is a big...
I'm not saying like teaching a whole course or something. Just getting a few people in front of it for a few hours.
So there's stuff we can do there.
Separate question is, what concessions have you already made to practicality in terms of not having to re-implement all of Win32 or .NET when you actually want to put this in a classroom so that you don't have to re-implement the graphics libraries.
Right. So again, library design is something I'm looking forward to getting onto probably next year when we've got an idea about what the module mechanisms that will let us talk to libraries will be. One thing that we put in the language was stolen shamelessly from F#, which is the backtick identifiers, so we will at least be able to write the identifiers to talk to .NET libraries. And maybe, if necessary, you could have a function and then metadata annotation that says, look, in .NET this really is something else, but our name has to be different because we're not overloaded and the .NET thing depends on being overloaded. That's as far as we've gone. I think the whole issue of library design is both important and really hard. It's particularly hard because at this point we haven't made a decision that we're going to stick to one platform. And certainly one of the big advantages of Scala, and one place where that differs from Grace is they said, right, well, and F#, I mean, they both made similar decisions on different platforms. We're going to cleave tightly to the model of a particular platform. And this means they, have got overloading and they've got to deal with the message semantics and they've got to deal with the object model, when in many cases you get the feeling they'd rather not. At this point we're saying, well, we'd really rather not. We'd really rather not say, if you're on the JVM, the generics aren't reified. Or if you're on either one of these, you have to deal with overloading. And we lied to you early on, which is what, fine. It'd be interesting to see how long that one holds up.
So what's the experience with languages that have these block arguments, which I guess are small talk, self, and so on, in terms of performance? I mean, is it something that can reasonably optimize away when you don't need the generality, or are you now locked into something that's just never going to perform reasonably well?
So if you've got really good compiler and VM people, like Craig Chambers and Ursula, then you can go faster than Java, or at least you could 20 years ago. The slightly more obvious thing is, well, we can do what Smalltalk does, which is basically, you're extending from Grace.standard environment, and these are messages on self, and we statically know that this may in fact be in the lexical chain, and we statically know that this if is the one that was defined because it's final and it hasn't been redefined, and our compiler can see that. Okay, so I mean that's what Squeak does, and that's what Squeak does. That's what Smalltalks generally do, and it's fine. And once again, there's this difference between the language and the implementation. You get into issues with this because one thing we say is, well, we're not necessarily interested in raw performance. We are interested in having a consistent performance model. And a performance model where, there's if, and if you really want to, you can define it yourself and your program runs 20 times slower. It's not really great.
So what do you do about the transition for students who complete this and now they're not transitioning just to Java, but they're actually transitioning to, let's say, the OS class where you can convince the professor to go into a memory managed language where they want C?
Which is all good.
What are the challenges, do you think, in the design of this language that will show up when you try to transition to something like C?
So our hope is that it will be no worse than Java. Really, and that's all we can say. And as much as possible, we're doing things to at least get people's eye in, if that makes sense. So this is where the language, the method I showed up, is not trying to be a million miles away from the sort of Java, C, C++ style. There's a keyword class, there's a class name, there's curly brackets, there are assignments that look pretty much like assignments. And so it goes. And we hope that people who's get some facility at reading Grace will be able to move and read C or the languages in what Ward Cunningham calls the curly bracket family without much trouble. And the answer is we won't really know until it's been out there for a while. But
there's something I'm wondering about, which I don't know if it surprises me or not. I think it does. It's going to take you 2-3 years to implement it. When you compile it for it?
Well, hopefully prototype implementations is this year. So, and it's in the middle of the year and we already have some prototype implementations. On one side, I think, one of the reasons why this is feasible to be done at this point without, vast amounts of institutional support from somewhere, although if anybody has institutional support, we're quite happy to accept it gratefully, is, when you look at stuff like, there's this tooling. So, on .NET, there's Visual Studio and there's a bunch of other things that let you put together languages quickly. And the speed at which you've been able to put Daphne and various things together and that other people have done so means, well, this doesn't have to take years. On the other side, we're working with students. The language spec is going to presumably be reasonably fluid, and it is fluid now for a while. And I think we're aware of the difference between a prototype implementation that works for research and something that we'd be happy to put in front of students.
Come from AP Computer Science where they've learned Java, what do you think you need to unteach or have them unlearn in order to be successful at Grace?
Well, we'll have to tell them to put colons before the equals sign for assignment. And spell out type names with uppercase letters always. And put do. And that's
semantic ideas that are just not appropriate.
Well, I don't really know how bad the model of AP computer science is, but I'm hoping it's basically, that semantic model should hold. I mean, what's the argument? I mean, argument that, well, you can switch from Java to C. If you're a Java programmer, you can switch to C# by just changing the syntax. I don't know whether that's probably not true anymore. There's now a lot more in C# than there is in Java. But to a first approximation, I would guess the distance is roughly the same.
Any other questions? Thanks, James.
I enjoyed giving the talk, and thank you for your time.